Okay, so continuing on with section 11.8, let's talk about the change of base formula. And it's used rarely in calculus, but you need to have it in your bag of tricks. And it says that if I have the log, say, base 7 of 15, then I can get a decimal approximation of that by doing the natural log of 15 over the natural log of 7. So the natural log of the argument divided by the natural log of the base. So let's make sure we can do that with a calculator, and the log base 5 of 37 is going to be the ln of 37 divided by the ln of 5. And I'm getting about 2.244 if I round to 3 decimal places. So section 4.4, it probably seems obvious, but we need to state the obvious sometimes so that we can use it as a fact. It says if you have two logarithms with the same base, then their arguments must be equal. And it goes the other way around too, that if you have two things that are equal and you take the logarithm of both of them, you'll still have an equality. So this first example, you just solve it by saying, well, I have the same base on both sides, the base of e, so that means I can just say that the arguments are equal, and then we totally know how to solve this. We'll subtract x from both sides and get 3 equals x minus 5, and then add 5 to both sides and get x equals 8. So the next one, you have to do a little work first because you need a single logarithm on the left-hand side before you can say log of this equals the log of that. So you're going to rewrite this with that quotient property of logarithms as 3x plus 1 over 5 plus x. And now you can say that the arguments have to be equal. Then the ln of 2 is just a number. So to solve this, we need to multiply by the 5 plus x. If what you're trying to solve for is ever in a denominator, you always need to multiply by the denominators. So on the left, they're going to cancel, and you'll have 3x plus 1 equals the ln of 2 times 5 plus x. And then we need to distribute and get 3x plus 1 equals 5 times the ln of 2 plus x times the ln of 2. Well, then I want to get everything with an x in it on one side, so I'm going to subtract x times the ln of 2, and I'll have 3x minus x ln of 2 plus 1 equals 5 ln of 2. And I'm going to subtract the 1 from both sides, so everything with an x is on one side, and everything that doesn't have an x is on the other side. And now I'm going to factor out the x. And divide both sides by 3 minus ln 2. So x equals 5 times the ln of 2 minus 1 over 3 minus the ln 2. So that's your final answer. Okay, if there are only logarithms on one side, then the trick is going to be to write it in exponential form. So let's first combine the logarithms into a single log. So it's going to be log of m over m plus 4. And that now equals -2. There is no log on the right-hand side. We're not seeing a base, so that means the base is 10. So we can write this in exponential form as 10 to the power of negative 2 equals m over m plus 4. So again, we're trying to solve for something that's in the denominator. So we should multiply both sides by m plus 4. And we'll have 10 to the negative 2m plus 4 times 10 to the negative 2 equals m. And again, we want to get everything with an m on one side. So 4 times 10 to the negative 2, that's 4 times 1/100th, so that's 4 100ths. And we're going to have m times 1 minus 1 over 100. So you're going to have 0.04 equals 0.99 m. So divide both sides by 0.99. And this is an exact answer. And then the approximate answer is 0.0404, and you'll see it's a repeating decimal. And then when we get to the end, we need to check just to make sure that we don't have a negative answer because we had the log of m in our original equation. If we had gotten a negative solution, we would have had to discard it. So when you're solving logarithmic equations, you must check all your answers in the original equation since the domain is arguments have to be positive. So whatever you're taking the log of has to be positive. So let's look at this next example. And I'm first going to get every logarithm on one side. So I'm going to have the ln of 2x plus 1 minus the ln of x minus 2 minus 1 equals 0. And then I want everything that doesn't have a logarithm in it on the other side. So I'll have the ln of 2x plus 1 minus the ln of x minus 2 equals 1. Write this as a single logarithm using that quotient property of logarithms. And then it's the natural log. So you don't see a base, but you know the base is e. So write it in exponential form. E to the 1 equals 2x plus 1 over x minus 2. And then what I want to solve for is in the denominator. So I'm going to multiply by x minus 2. And then I'm going to distribute this e, get x times e minus 2e equals 2x plus 1. Then my strategy is going to be get everything with an x on one side and everything that doesn't have an x on the other side. So I'm going to subtract 2x from both sides. And then add 2e to both sides. Factor out the x. and divide both sides by e minus 2. And you'll get your final answer that x equals 1 plus 2e over e minus 2. And then we should check our answer to make sure it's not going to make a negative input to a logarithm. So this is about 0.718. So if I come back to the beginning, 0.718 minus 2 gives me a negative result. So this answer has to be discarded. And actually, let me double check because I'm not liking my answer there. Oh, take it back. Let me try one more time, make sure I get the same thing twice. So I have e times 2 and add 1. Then e minus 2 and divide that. Now I'm getting a better number, 8.96. So we go back to the original problem, and 8.96 is fine here, and 8.96 is fine here. Okay, so let's look at another example. So the strategy is going to be to combine the logarithms into a single logarithm. And here we have the product property of logarithms. And we have a base of a. So when I write this in exponential form, it's going to look like a to the 0 equals 4x minus 7 times x squared plus 4. Well, a to the 0 is 1. So I'll have 1 equals 4x cubed plus 16x minus 7x squared minus 28. And I need to subtract 1 from both sides. So I'll get 4x cubed plus 16x minus 7x squared minus 29 equals 0. So that solving that equation would give you all the possible values of x. And this is not something that I would ask you to do on a test. And in fact, I'm not really sure how they expect you to do it on a homework problem. Because let's look at what it would look like in Desmos. We have 4x cubed plus 16x so 4x cubed plus 16x minus 7x squared minus 29. So what we want to know is if there's any zeros. Well, I'm only seeing 1 here. And 1.785, this is the only way I can see that you could find that. So I would not expect you to be able to solve this on a test. Quadratics, I expect you to be able to solve, and cubics if they work with factor by grouping, which this one doesn't. Okay, so let's do One more example of solving an exponential equation using logarithms. And I picked the ln because the bases don't match here. So I'm just going to use the ln. And then I use the property of logarithms that says this exponent can come down in the front. Make sure and keep it gathered together with parentheses. And this exponent can come down in the front. And now we need to solve for x. So if x is in parentheses, we need to distribute to get it out of the parentheses. So I'll have x times the ln of 4 plus 2 times the ln of 4 equals x times the ln of 5 minus ln of 5. So now I want to get everything with an x in it on one side and everything that doesn't have an x on the other side. So I'm going to subtract x ln 5 from both sides and subtract 2 ln 4 from both sides. So I subtracted the x ln 5 from both sides and subtracted 2 ln of 4. So then I'm going to factor out the x and have ln 4 minus ln 5. Then divide both sides by the ln of 4 minus the ln of 5. And this could be simplified some using properties of logarithms, because I can see that ln of 4 to the negative 2, that could be simplified. And then minus ln of 5, I can put those together and simplify. And then in the denominator, I could have the ln of 4/5. So in the numerator, I'd have the ln of 1/16 minus the ln of 5 over ln of 4/5, which would be the ln of 1 over 80 over the ln of 4/5. So this answer is fine. Sometimes in the book they go farther, so know that that's all they're doing. Okay, so I'm going to go ahead and pause so that the movie's not too long, and I'll continue on.